On behalf of the Center for Occupational Environmental Health, I'd like to welcome you to today's webinar on the topic of green chemicals and chemical policy with Dr. Megan Schwarzman. Before we get started, I'd just like to go over a few housekeeping items. You will be muted during this presentation, so if you'd like to ask a question, please enter it into the online chat or Q&A, and at the completion of the presentation, the presenter will spend 5 to 10 minutes answering your questions. So anytime you have a question, please feel free to enter it, but we will be saving them to the end. There is one continuing education contact hour available for this webinar for a fee of $30. If you wish to obtain credit, please register again at coeh.berkeley.edu and then complete the evaluation for the webinar. You'll then be emailed your certificate of completion. After today, the webinar will be archived on our YouTube channel, so you'll be able to watch it or share with anyone you'd like to see it. The webinar is also currently being live streamed on Facebook. So at this time, I'm very pleased to be able to welcome our presenter today, Dr. Megan Schwarzman. She is a physician, a researcher, and an environmental health scientist at UC Berkeley School of Public Health, and she's also Associate Director of Health and Environment for the Berkeley Center for Green Chemistry. We're very, very pleased and honored to be able to have Dr. Schwarzman present today, and on behalf of COEH, I'm pleased to welcome her to the webinar today. Welcome.
Thanks so much. I appreciate your having me. As Julia said, I'm going to talk for about 45 or 50 minutes, and then I'm happy to have comments and questions after that. My work in the Environmental Health Sciences Division at UC Berkeley is mainly looking at the science of harm from synthetic chemicals and pollutants. And my goal of that is basically to do two things. One is to make it visible. If we think of sort of two parameters, in physics, there's like energy and there's matter. And there's a lot of attention currently around climate change on energy, and there's significantly less attention, I think, on matter. And that's the materials that make up our daily life. So part of it is to make it visible, to improve our understanding of newly emerging mechanisms of action, particularly endocrine disruptors, and I study the role of the environment in breast cancer, for one thing. And the second piece is working to align the drivers to create change. And this is largely what I'm going to talk about today, because if our goal is making the material basis of society significantly safer, then that's going to require a fair amount of change. And so what can we do to drive that change toward green chemistry? So today I'm going to tell you a tiny bit about how I got from being a physician to being in environmental health sciences. And then I'm going to give you a little bit of illustration just as background for those who aren't super familiar with green chemistry, to sort of the case for green chemistry, and give a few examples of some solutions. I'll propose some solutions and give some examples of places those are being implemented in the world. So this is a picture that looks out from my clinic where I did my outpatient work in family medicine in San Francisco. So I was at San Francisco General through UCSF for my family medicine residency in the early 2000s, and I did an outpatient clinic at Potrero Hill Health Center, which had roughly this view out over, you can see in the foreground, the Potrero Hill housing project, and then warehouses, bus depots, and then finally a freeway. And what you can't see behind the photographer here is another freeway. So it's ringed by 101 and 280. And what I saw in my patients really reflected this environment. I took care of a lot of families with kids with asthma and other diseases that felt like they were significantly contributed to by the environment. And I could prescribe medications, but I wasn't doing much to prevent potential causes of the disease I was seeing. Here's a picture from a different angle. of some of the neighborhoods that my patients came from, where children were twice as likely to be hospitalized for asthma as other kids just in San Francisco. And the overall hospitalization rates for chronic illness were 4 times statewide averages. In Bayview Hunters Point, which was part of the sort of catchment area for my clinic, it's the most industrialized neighborhood in San Francisco. It has the dubious claim of having 1/3 of the city's hazardous waste sites and 2 Superfund sites, the highest concentrations of monitored air pollutants, and 1 in 6 children in Bayview Hunters Point is diagnosed with asthma. So I sort of felt like I was trying to catch a tidal wave in a teacup, and wanted to go a little bit more to the source. And so I came back for my environmental health sciences degree in the School of Public Health at UC Berkeley, and then from there got involved in the field of green chemistry and have been here ever since. I still do some clinical work, but it's a relatively small piece of my weeks these days. So just for basic orientation, the term green chemistry was originated at US EPA and then sort of codified in this book, Green Chemistry Theory and Practice by Paul Anastas and John Warner in the late 90s. And it's summarized as the design of chemical processes and products that reduce or eliminate the use or generation of hazardous substances. And it's meant to apply across the life cycle of a chemical product, from its initial design through its synthesis or manufacture and use, and then ultimately disposal. And so these are the 12 principles of green chemistry as articulated by Paul Anastas and John Warner. And I highlighted the ones in blue that have to do with safer chemistry, because green chemistry actually includes a fairly broad range of sort of mechanisms for change, and some of it really has to do with efficiency. The ones in gray here are actually maximizing atom economy, decreasing the material throughput and the energy consumption, and decreasing the use of non-renewable feedstocks and things like that that are meant to increase the efficiency of chemical reactions. The ones in blue here are a little more about preventing pollution and moving toward inherently safer chemistry. Designing for degradation is to do with making sure that chemicals that get into the environment don't stay there for decades or years. So this is a very interesting kind of framing of a new field. The place where this doesn't, where it's not very illuminating is sort of what constitutes safer. How do you make a less toxic synthetic process? How do you prevent waste? And so there's a whole field that has grown up around sort of putting the meat on these bones, figuring out what constitutes a safer chemical, and then furthermore, policy related to implementing green chemistry. How do we stimulate the development and adoption of safer chemical processes and products? So the case for green chemistry. The first piece is simply sort of the volume and ubiquity of synthetic chemicals in our society. The tankers on the left are just meant to depict the volume of chemicals, synthetic chemicals, industrial chemicals that are produced and used in the US every day, which is 72 billion pounds per day of what's produced or used in the US. This is only considering industrial chemicals that are governed by the Toxic Substances Control Act. So it's not actually fuels. This is a little bit of a misleading comparison, but in any case, I'll explain. It doesn't include fuels or pesticides or pharmaceutical chemistry. So if you converted that 72 billion pounds a day into gallons of water, which is an approximate conversion because of mass differences, but in any case, it would fill up enough of these tanker trucks to line up end to end 10,500 miles. So that's daily production or importation of industrial chemicals in the US. By no means are all of these hazardous chemicals, and there's a very wide range, and some large volume of these chemicals are presumably quite safe, but it's just to say that what we're dealing with here is a tremendous part of the economy and a tremendous mass of materials. What we're producing and using now is projected to grow very dramatically. So we did a comparison indexing to the year 2000, comparing projected global chemical production in the blue bars to projected global population growth over the subsequent 50 years. And you can see that, while we think of global population as kind of expanding, exponentially and potentially out of control, global chemical production is at least projected to increase much more rapidly. That's a 25-year doubling time of about 3% per year growth. And they're not only produced, but so it's not, chemicals don't just show up in industrial processes and manufacturing. They're also used in a whole variety of consumer products, but also the material basis of our world: building materials, electronics, furniture, food, clothing, cleaners, toys, etc. Some chemicals undergo long-range transport, which is why we see precipitation of persistent organic pollutants over the poles where they are not used, and their concentration in particularly aquatic species at the top of the food chain. Some persist or bioaccumulate, which leads to their accumulation in the environment also. Many are in consumer products, as I've just mentioned. And for the average consumer, which is not the people on this call, I think there's a false sense of security that if it's sold, somebody must be checking and making sure that it's safe. The other point is, I often get asked, but haven't we evolved to kind of cope with these chemicals? But in truth, all of these compounds, whether they're hazardous or not, are new to human biology, that the scales here are millions of years different, that human evolution compared to modern post-World War II chemical production. And some of these compounds, as we're seeing with the emerging science around endocrine disruptors, really have the potential for multi-generational effects, that there's epigenetic changes in the ways that genes are expressed. There's changes to germ cells. If a developing fetus is exposed in utero, there's changes to the germ cells that then pass changes along to future generations, whether those subsequent generations are exposed or not. So this combination of volume, some known hazard, a lot of unknown, and the potential for persistence in the environment, bioaccumulation through the food chains, and potential for multi-generational effects is kind of stacks up to something that we need to pay attention to. A second element of the case for green chemistry is that a lot of these compounds show up both in the environment and then, obviously not surprisingly, in people. We did a survey through California EPA did a survey of their hazardous waste sites, and 61 out of 85 of the largest hazardous waste sites were leaking directly into groundwater, and they determined that 94% of those posed what they called a major threat to human health or the environment. So this notion that we can use hazardous chemicals because we can safely store them and we can make them go away is fundamentally, I think, a flawed notion. And then, many people are familiar with biomonitoring data done both with a nationally representative sample of the US population through the CDC NHANES biomonitoring program, but also done here in California and through individual scientific studies that look at, say, umbilical cord blood or breast milk. And this is just a small selection of some of the compounds that are found. These in particular that I highlighted were found in over high 90% of umbilical cord blood or pregnant women in the NHANES biomonitoring study. So these are obviously compounds that we know we wouldn't want to expose the developing fetus to, and yet we know that they're there. A third case for green chemistry is the area that's very familiar to most of the people on this call, and that is workplace chemical hazards. Just looking at a tiny slice of this, we know that there are at least 60,000 premature deaths per year that are attributable to occupational diseases. It's probably from chemical exposure. So this is not counting traumatic deaths or accidents, and it's only counting a few outcomes like chronic obstructive pulmonary disease, asthma, some cancers that are known to be associated with workplace chemical exposures. So this is a very, it's an old number for one, but it's the only number that still exists like this, and it's also very limited counting. We think of workplaces as fairly controlled, and specifically that we have a good handle on what's an allowable exposure limit through our national and state set permissible exposure limits for workplace exposures. And yet, if you just look at the 3,000 high production volume chemicals, which are those produced or used at over 1 million pounds a year, we only have set PELs for 7% of those. So production volume is a surrogate for potential exposure. It doesn't say anything in and of itself except we use a lot of it and we produce a lot of it. It doesn't mean that it's hazardous per se, but we use a lot of it. And so presumably, even if some small proportion of those were significantly hazardous, we've only studied and set permissible exposure limits for 7% of those. And in general, we all know there's sort of a tendency that if you don't measure it, it doesn't exist in terms of kind of controlling workplace hazards. OEHA, California EPA OEHA, looked at some common workplace chemicals and calculated the cancer risk for exposure at the PEL and found that for 6 of them, the cancer risk was 1 in 10 for exposure at the PEL. So this suggests to me that even at the permissible exposure limit for those chemicals for which someone has designated a permissible exposure limit, we still are exposing workers to too much of carcinogenic chemicals. And of course, immigrants and minorities and low-income workers are often disproportionately represented in some of the highest chemically intensive work types or jobs within workplaces. So one final illustration of the case for green chemistry is a story that people who are in the Bay Area certainly, and many people involved in industrial hygiene are familiar with, which is the haphazard history of substitution that we saw in the field of solvents used in the automotive repair industry. This is just sort of a cautionary tale where we saw a 30-year history of serial substitutions that were made in brake cleaners, starting in the 1970s when the started solvent was eliminated because it was a fire hazard, through a series of chlorinated solvents, which were phased out in the 1990s because of a very clever, I think, sort of piece of detective work by the California Air Resources Board, which traced dioxin emissions to contamination of the used oil supply with chlorinated solvents. So as in this picture, somebody's doing a brake job, the chlorinated solvent is dripping off into the waste pan, and same waste pan that collects, used oil from oil changes. And then that oil was combusted as bunker sea fuel in ships. And so coming and going from, say, the Oakland Port or the LA, Long Beach harbor, when you combust chlorinated materials, it produces dioxins. And so California Air Resources Board phased out chlorinated solvents, but they didn't suggest what should be used in their place. And without a planned substitution, that gap was filled by hexanes, which are very safe. Not very safe. They're very effective and inexpensive. And some of the formulations were about 90% hexanes. And because of VOC's contributions to ground level ozone formation, the California Air Resources Board said none of these formulations can be more than 50% VOCs, but they exempted acetone. So there's another inexpensive and effective solvent. So this produced these hexane and acetone blends that turned out to be uniquely toxic. So this was discovered in the early 2000s. There were some index cases seen by Bob Harrison at UCSF of young automotive repair workers who had lost sensation and strength in their hands and feet. They were dropping their tools. One was wheelchair bound. And it was traced to these hexane acetone blend brake cleaners. So this is just a cautionary tale. And then those were, HESIS issued a health hazard alert. And some formulations went to heptanes, which are probably significantly safer, but some went to 1-bromopropane, which is a known reproductive toxicant. Male workers synthesizing 1-bromopropane in a in the use for use in pesticides were sterilized by this. So there's this sort of, this is just one illustration, and we could choose other kind of examples of this as a cautionary tale, and it really reflects many flaws in the system. One is the historic tendency to address any particular harm in isolation without looking at the larger context of what it might be replaced with, how it's used. And the other is that it's sort of created, this situation is created or perpetuated by the siloing of expertise, that Air Board did this very clever work to figure out where dioxin emissions were coming from, and their intervention generated a serious occupational hazard. So, you know, some other interesting things that came of this when you actually talk to the manufacturers who were producing these hexane acetone blends, they said several things. One was that, well, it works really, really well. Another is that workers could be protected. And finally, that they just didn't realize that people were going to be using so much, that the automotive repair workers were going through 8 to 10 cans of this in a day. And that just points to all kinds of places that were missing elements of the system that we could be doing better. One of the other key origins of these kinds of flaws was in the federal oversight of chemicals, namely in the Toxic Substances Control Act. And it had great objectives when it was passed. This is in the preamble, or in the sort of objectives outlined within Section 2 of TSCA Section 2, that chemical producers should develop good data on health and environmental effects of chemicals and mixtures, that government should have adequate authority to regulate chemicals that present an unreasonable risk to health or the environment, and that government's authority shouldn't create economic barriers to innovation. But what we saw, in fact, was that TSCA failed. We have articulated in the past the 3 policy gaps that I'm not going to belabor here, but we basically divided it into the lack of information that TSCA had aimed to produce but failed at, and it has to do with how chemicals were grandfathered in without data requirements, that a higher bar was set for new chemicals than for old, and yet those data weren't reviewed by EPA, and the default was that they go to market, and that basically EPA was unable to request data without proving risk first, and so it put them in this catch-22. The safety gap was meant to describe how EPA didn't end up with significant authority or sufficient authority to govern chemicals that they discovered as at high risk, because of this inclusive phrase that's in TSCA Section 6 outlined here, that EPA has to provide all of these things: substantial evidence of risk, that benefits of regulation outweigh the cost to industry, and that EPA has chosen the least burdensome solution. And sort of laboring under those burdens, TSCA formally regulated 5 chemicals or classes using their authorities under TSCA in the time before it was reformed in 2016. And the third piece of this was we described as the technology gap, which was that this absence of data and the difficulty in calling out and taking action on imminent hazards meant that, you know, as the third goal here was to not create unnecessary barriers to innovation. And in fact, the ultimate outcome was that it did create barriers. There were no incentives for generating safer, less hazardous chemicals, and we called that basically a market failure. So, as you know, TSCA was reformed. It is still sort of going through implementation. I think the reform addressed a couple of these failures, but not completely, and it looks like implementation is actually not playing out at this point in a way that would significantly address some of these gaps, or at least too slowly to kind of be appreciable at this moment. So the outcomes of this current decision-making structure at many levels are illustrated by just two examples. One, really well known, was that EPA first tried to use its authority under TSCA to regulate some uses of asbestos, and they spent 10 years and generated, linear feet of documents stacked up, and that attempt to regulate it was overturned by a court of appeals, basically ruling that EPA didn't meet its burdens of proof on this that are detailed here, but under the safety gap, including that they hadn't chosen the least burdensome solution. So industry effectively argued that there were less burdensome ways of controlling the use of asbestos, and at that point EPA basically gave up. The second outcome of current decision-making structures that I would flag is how dependent we are on the risk assessment process, and how far the risk assessment process tends to lag behind the science. And I'm not going to go into this in detail, but just to sort of point toward how in the past decade, the science on the impacts of low dose exposures to bisphenol A and other endocrine disruptors, but BPA is often sort of the poster child for this, has been very slow to be reflected in any kind of regulatory science. But it makes me ask the question of, even if we did get to the bottom of the scientific debates about bisphenol A and its harm, sort of then what? We return to the example of the brake fluids, of what would be replacing BPA. What about the tens of thousands of other chemicals in commerce? How do we know what's safe? How do we define something that's safer? How should we be making these decisions as a society? And how can we incentivize the development and adoption of safer alternatives? And so this really gets to kind of, how do we start shifting the pendulum and kind of incentivize and move market forces to incentivize the development and adoption of safer alternatives? And I'm going to offer a few solutions. First, a little bit theoretical, and then give you some examples of where this is happening a little bit. So one solution is to make safety a design parameter. So typically, to this point, regulation has produced a world in the chemical and product space in which what drives chemical design or selection are three factors, basically: price, function, and performance. How much does it cost? What is it meant to do? And how well does it do that job? And this has led us to consider the health and environmental impacts of chemicals basically as kind of the last hurdle to innovation in developing a new substance, or it's what we discover long after a chemical has been significantly used, released into the environment, people have been exposed. And so to make this comparison, I have cars here for a reason, because when we started requiring safety measures like seat belts and other safety measures in cars, at first the automotive industry really objected that it was going to make cars too expensive. People didn't want it. People were not going to buy their product. And what we've seen actually in retrospect is that it did two things. One is it kind of created a niche market for brands to start marketing themselves as the safer car. Like we saw the emergence of Volvo as kind of the one that got the household name as the safest car, where, if you wanted a cheap car, you could buy a Datsun. If you needed to go camping, you could get a camper van. And if you really care about high performance, you might get a Porsche. But in any case, it defined this fourth category of the safe car and allowed consumers who wanted to choose a particularly safe car to do so, because it made that transparent. It made that a design parameter. And some companies decided to start marketing on the basis of that design parameter. And then the other thing that it did was it raised the bar for all cars. And it turns out, of course, that it became the norm, and all cars got a lot safer. And per number of highway miles or road miles traveled, fatalities have gone down significantly with the introduction of safety measures. So I think this kind of evolution of a field is possible, but what we have to do is move hazard assessment to a much earlier place, back to chemicals, in the design process. And doing so makes safety a performance criterion. It makes it a design challenge on a par with technical performance. And that gets the interest of chemical engineers and chemists, because it's what they do, is they solve problems with chemistry. And so I think it's possible with a reorientation to do this. So how do you start informing the design of safer substances? You start asking questions differently. Instead of, how do we just keep making the electronics we're making, you might say, what would a chemical look like that doesn't migrate from electronics, building materials, or packaging? If we're thinking flame retardants or plasticizing chemicals. What would a chemical look like that isn't taken up through dermal contact or doesn't accumulate in food webs? How can products be flexible without phthalates, or stain resistant without fluorinated surfactants, or flame retardant without halogenated compounds? And what are the safer alternatives? And they could be chemical or they could be material. And we've seen this with flame retardants once companies were freed up from a really restrictive flame retardancy standard, then they had the leeway to design inherently flame retardant materials and just select already existing inherently flame retardant materials and avoid adding chemicals to polyurethane foam. Likewise, carpets are now being made to be stain resistant without adding any fluorinated surfactants by having redesigned the shape of the fiber. So if most commercial carpets are made from polymer fibers, so that are extruded, they're not spun like a natural fiber, they're extruded. And if you change the shape of the nozzle and make that cross-sectional shape of the fiber different, it doesn't hang on to stains and dirt. And so you can make it inherently sort of stain resistant and dirt shedding without adding a fluorinated surfactant. So I think if you ask the question differently and frame the sort of safety as a piece of technical performance, you get very different answers to your questions. Another piece, another potential solution is sort of a challenge for the environmental health sciences of how to generate data that is relevant to chemical and product designers. This is a little sketch I made because I can go kind of crazy in PowerPoint trying to create a diagram. And so I just sketched it and included it as a photograph to depict. At the left-hand side is sort of where environmental health sciences typically lives, studying chemicals that are used in agriculture or industry or the built environment, pollutants that are generated through mobile sources. The left bottom corner is meant to be like personal care products and food, and then sort of their impact on people, children and adults. And then if we sort of move through this hierarchy from the left to the right through animal testing and more predictive, so these are meant to depict molecular mechanisms on smaller organisms and get to the point where we're finding mechanistic information, then that's a lot closer to chemical design. That's just a totally generic chemical, not to point fingers toward any particular chemical. So the challenge, I think, is to start generating mechanistic information that helps us bridge the gap between the evidence that has been typically generated by environmental health scientists and produce evidence that's a little bit closer to what's needed by chemical designers and people choosing material selection, choosing materials for particular applications. So I think this is a challenge that is being taken up by pairing environmental scientists and toxicologists with chemists and engineers, and I'll give some examples of where that's happening. So another solution is to make decisions in context. This is what was obviously missing in some of the sort of histories of regrettable substitutions. And one example of a split between sort of contextualized and not so contextualized decision making is the contrast between risk assessment and alternatives assessment, which arguably have different applications, and you can certainly use risk assessment data in performing an alternatives assessment, can be very helpful, but it also has some limitations. And I just want to point out some of the contrasts here, where risk assessment asks what's an acceptable level of harm. For example, how many cancers might be caused per 1,000 or million people, and considers activities in isolation. So does this one use of this chemical contribute significantly to disease? And then asks, does this activity or product fall within that acceptable level? Alternatives assessment would compare many approaches to accomplishing the same function, and then ask the question, is this potentially hazardous activity or product necessary? How little damage is possible? And what other options are available? And I'll give some examples of how that's being done. So my fourth solution, before I move on to examples, is in training interdisciplinary scientists. And this is a photograph from one of our groups in our Greener Solutions graduate program here at UC Berkeley. And this is a group of chemists and engineers and architects and environmental health scientists learning a bit about biomimicry, and they loved it because they were outside. But one of the things that we're doing here at Cal is trying to train sort of a next generation of scientists who understand the context that they're working in. So our goal is not to create chemists and engineers who are also toxicologists, but that they understand that toxicology exists and what some of the considerations are and know to ask the questions. So this leads me to my first example, which is the Greener Solutions program at UC Berkeley. This is one of our first days of a class year where we have them do some team building exercises, because they're going to do a lot of hard work in an interdisciplinary team over the course of the semester, and we do a little bridge building first. So what the Greener Solutions class does is we partner with a company who is seeking to basically substitute out some hazardous chemical that's in their product or process. And we work for the semester on trying to find a safer alternative. So a couple of years ago, we were partnering with Patagonia, Steelcase, and Mango Materials. Patagonia was asking how could they make an inherently mosquito repellent clothing, and both Steelcase and Mango Materials had challenges around coloring polymers, because colorants and dyes can often be quite hazardous and get into the environment. So the first thing that we do is define the chemical function really carefully. How do you accomplish mosquito repellency? How do mosquitoes detect people? Through CO2 plumes and heat. And so what this chemical is doing is, killing the mosquito or confusing the mosquito, et cetera. So we're defining chemical function really carefully, and then looking at the application that the partner has given us and understanding the design constraints. So for example, with Patagonia, they were looking primarily to treat or create synthetic fabrics that were mosquito repellent. So that's really different than working on cotton in thinking about chemistries and weaves. And to understand how these products are manufactured in great detail so that we understand how to work within that technical system. And then the next step is to identify alternatives. And one of the places that we send them is to biology, send the students. So we train them in bio-inspired design, taking their chemical function and saying, okay, how does nature do this? How does nature make things colored? How does nature how do animals deter mosquito, or plants? Are there plants that have insecticidal functions, and how do they do it? And then it's not the only place they turn, but one of the things they ask is, how does biology do this function? And then they do a pretty comprehensive hazard assessment based on function. How well does their proposed solution function according to a bunch of performance parameters, and how is its relative hazard? And what they end up with is this opportunity map. So we don't do any lab testing during the semester, but we try to basically sketch out where the company might look for solutions. And just to say one note about this, this is all pre-competitive work. So as a public university, we're not signing non-disclosure agreements. We're not doing research that would give any of these companies a competitive advantage. We're often working on problems that are common to an industry sector, that sort of plague everybody in that industry sector, and that would be well served by solving them and spreading them among everybody in that industry sector. And all of the products of our work are publicly available. Often as a guide for the hazard evaluation, we use the parameters developed by the Green Screen for Safer Chemicals. I'm going to give you a couple examples of some recent work by the Greener Solutions students, and I'm going to move through these quickly just so we can get on to next examples, but just to give you a little glimpse of what these kind of opportunity maps look at. One of them was working on safer preservatives for personal care products, and they looked at existing product formulations and then potential inspirations from biology, pulling out structural and functional themes, and then seeing what the design constraints were in terms of physical chemical properties and antimicrobial potency, and then assessing health hazards. So they identified several biological sources of potentially promising compounds, including terpenes, flavonoids, fatty acids, and peptides. And they developed this sort of multi-criteria evaluation framework looking at hazard, antimicrobial efficiency, trying to categorize the level of uncertainty, looking at biodegradability, the origin of raw materials, compatibility with the current product, so how readily substitutable that solution is, and any potential regulatory concerns, and then a quick estimate of cost, which is hard to do at this stage. And basically, as you can see here, 3 constitutes a better score than 1. And so this is kind of one of their charts from their final reports. This was for 7th generation. Their chart looked a little different for the other partners because they had different priorities. But you can see that there's a range here, but you start to get a picture of some of the, they were comparing it to methyl isothiazolinone, sorry, it's a long one, was the sort of baseline that they were trying to eliminate, and identified some potential solutions that were less hazardous and even a better fit. So some of the students from this went on and got the opportunity to do some testing, and based on some of the inspiration that they had from that project, developed other possibilities and published this paper recently on a potentially safer preservative in several applications. You can see this is home and personal care products, food packaging, and building materials. And these spider diagrams just are a summary of their relative effectiveness and their toxicity, and the smaller values closer to the center indicate better performance on that metric, and octyl gallate here at the top of each of these keys is the safer alternative that they identified. We did a project also recently on safer spray foam insulation that was linked to its designation as a priority product under California's Safer Consumer Product Regulations, which I'll talk about in a minute. I'm not going to belabor this just for time, but they came up with some potential alternatives. Everything from a fairly easy drop-in solution of polymeric MDI, which should be less bioavailable, to an existing product foamed concrete, to some out there pipeline solution kinds of things, using biology as an inspiration for protein cross-linking, polysaccharide cross-linking, and pH-influenced cross-linking. They evaluated their function, they evaluated their hazard, and produced this summary table that compared function and hazard, and also found a way to try to express the kind of range of uncertainty. And they went on to publish this as not only their findings from the work, but also as having created the framework for a simultaneous evaluation of function and safety. So the second example that I'm going to give is California's Safer Consumer Products Regulation, which has this multi sort of tier path of developing a candidate chemical list and choosing from that list priority chemical product combinations that may cause harm, from that requiring manufacturers to do an evaluation of alternatives, and then DTSC will consider a range of possible responses. And the key mechanisms in this that I flag because they address some of the problems that I've raised are first the chemical list, the fact of priority product selection, the work plan that they generate, the alternatives assessment, and the petition process. And I'm going to go through each of these just briefly. So in writing the Safer Consumer Products Regulations, DTSC made a very conscious choice to create a large list of candidate chemicals. And that produces sort of two leverage points. It produces change in two ways. One is through general deterrence. So if there's a long list of chemicals, a lot of products potentially fall under that list, as someday these may be designated. These may be flagged for, if this is in your product, you might want to look at whether there's a safer alternative. And KP Public Affairs published a brochure to their clients that said it's neither necessary nor prudent to wait for products to be listed under the Safer Consumer Products Regulations to undertake proactive compliance measures that will mitigate potential costs and liabilities for current products, increase market competitiveness, and enhance your sector leadership through innovation. So this, to me, is really calling out the sort of pre-regulatory effect of a large list of candidate chemicals, saying you can get ahead of the game, you will increase your market share, you'll do more innovation. If you don't wait for your product to be listed and your chemical to be identified from this long list of a couple thousand candidate chemicals, just get ahead of the game. And then this is sort of the sense that it creates the demand for green chemistry solutions for safer alternatives, even in the absence of direct regulation of any particular chemical. So that's the role of the large candidate chemical list. Then there's priority products that are designated. They're up to 3 to 5 per year, but in fact, it's been quite a few years, and these are the 3 that are established in regulation now, and another just came out. So they're chlorinated tris in children's nap mats, diisocyanates in spray polyurethane foam insulation, and methylene chloride in paint strippers. And so for these priority products, producers now are on a timeline for having to perform an alternatives assessment and try to find safer alternatives to these hazardous chemicals in these applications. So that's more of a direct regulation that will emerge. Once they submit an alternatives assessment, DTSC will base their regulatory response on the findings in that alternatives assessment. This is the latest priority product to be named. It's draft because it goes through the regulatory process. But I raise this because it's significant, because it's the first time in many places that a whole category of chemicals, a whole class of chemicals, PFASs, has been named, and that DTSC is naming them as a priority product in carpets and rugs. Because if you just call out a couple perfluorinated compounds, it's too common for the industry to move easily to a drop-in substitute that may or may not be safer, as we've seen with our sort of history of serial substitutions that turn out to not have been a good idea. So that's an influential piece of this priority product that has just been named and is currently open for public comment. The work plan was the next item on my list, and every 3 years, DTSC publishes a work plan under these regulations. They just published their next work plan for 2018 to 2020, and they designated the same categories as had been in the previous work plan, plus food packaging and lead acid batteries. And the impact of this work plan is twofold. One is it provides some predictability to the industry to say, we're not going to sneak up on you. These are the categories of products that we might consider in the next few years. And so if you make one of these products and it contains a candidate chemical, you should start thinking about that now, talking to your suppliers, figuring out whether it might fall under this regulation if we decide to name a priority product in this category. So it provides some predictability, gives the industry some time to anticipate, and again, kind of this general deterrence function of all of the makers of these kinds of products are potentially going to start asking the question now, do we have known hazardous chemicals in our products, chemicals that are named on the list of candidate chemicals, and gets them to start thinking about it. And what they start thinking about it is alternatives. So the main function of this regulation is that instead of banning a chemical, irrespective of the availability of safer alternatives, manufacturers have to ask, is it necessary, and is there a safer alternative? And the final mechanism that I wanted to flag with the SAP regulation is the petition process. So on the CalSafer website, you can submit, I just flagged this, submit a petition. Either you can petition adding a chemical to the candidate chemical list, or you can submit a petition for a product chemical list, product chemical combination to be prioritized. You can also submit if you know about a safer alternative. So in this way, there's kind of a wiki commons aspect to the regulation that might be productive. The final example that I want to give very quickly is one place where the precautionary principle has been put into decision-making in the city of San Francisco, and this is courtesy of Debbie Raffel's work there and her slides on it. They wanted to look at their use of the herbicide Roundup, glyphosate, and they, asked the question, of course, is it legal? It is. Is it safe? There's tremendously conflicting evidence. And so they asked the question, is it necessary? And this was because San Francisco has a precautionary principle ordinance, a precautionary decision-making ordinance. And so they said, well, how do we address this issue using the precautionary principle? And they gathered the gardeners together and said, well, where do you use it? And the answer was this list of uses: natural areas, private lawns, public parks, built environments, airport runways, etc. And then they said, well, what are the alternatives? And came up with this list of hand weeding, using the flame torch, my favorite, using compost tea, which is what this big tub is. The other picture is of the Conservatory of Flowers, where they said, well, in some places we could kind of tolerate wet meadows instead of having perfect lawns, and then goats for weeding, essentially. And the result of asking these questions was a 90% reduction in their use of glyphosate in San Francisco, because they eliminated what they decided were unnecessary uses. They used goats and hand weeding and flamers and compost tea where it was possible. They prevented weeds with mulch and sealing cracks, and in some places they accepted this idea of meadows and not lawns. And what I thought was particularly interesting were the places that they decided to keep the herbicide use because it was the least harmful alternative. And those included median strips, where if you put a worker out there flaming weeds, that could be a pretty dangerous spot for the worker. They decided it was the least harmful alternative in removing invasives from some natural areas. And then you can't shut down SFO to graze goats. So they still use it on the airport runways. So this just highlights the way that you can do decision-making that acknowledges uncertainty and ignorance. This is from some really valuable work, I think, by David G. and colleagues in the European Environmental Agency on late lessons from early warnings that is really worth looking into. They flag some criteria for precautionary action that gives you a sense of how you might make decisions in the face of uncertainty, and in a way that respects our ignorance, actually, for all of the unknowns and our capacity for surprises, like we saw with the serial substitutions of brake cleaners. So I want to end there with some ideas about how people might make decisions a little bit differently than we have in the past, and invite any questions or comments.
Thank you so much for that presentation. Just a reminder to everyone, we have a few minutes for Q&A, and if you can either enter it into the Q&A section or into chat. We have one question that goes back to the very beginning of your presentation about which of the 6 workplace chemicals posing risk at for OSHA PEL?
Yeah, I actually need to send you for that too. I have the report here on the slide. Sorry, I have to go back through all of these. Teach me to animate my slides. Makes it hard to move around. This has the, I don't have the chemical names at the tip of my fingertips, but they're in this oh, you know what? It's the numbers are switched there. That's I'll switch those footnote numbers because it's the Cal EPA OEHA report from 2009 that names those 6 workplace chemicals. So I'll straighten out that reference before I send my slides to Julia.
Yes, and we'll be sharing a copy of the slides with everybody who attended today, so we will get that reference to look it up. While we're waiting for some other questions to come in, I was wondering whether there are regulations like the Safe Consumer Products in California in other states, and sort of nationally. Is that something extraordinary or pretty usual?
At this point, it's something extraordinary. It's actually remarkable and worth mentioning. The reason I go into it at some depth is because it's the first place that alternatives assessment has actually been codified in regulation. And I think it's particularly striking because it's the first time a state has tried to take on this issue of regrettable substitutions, of having made substitution because of a specific hazard that was identified, and yet doing that substitution in a way that shifts risk, maybe from one medium to another. You know, the way MTBE was used in California, trying to clean up the air, but ended up polluting the water seriously. So that kind of risk shifting that goes from one population to another, or one medium, environmental medium to another, history is just rife with those. And so this attempt to put decision-making in the context of an assessment of alternatives and looking not just at hazard impacts, but also, are there trade-offs here that would substantially increase energy use, right? So you don't want to decrease hazard and increase the production of greenhouse gases, for example. So it's trying out this approach of making these decisions much more firmly rooted in context, specifically trying to avoid making those kinds of mistakes we've made in the past. So it's the only place where that is really at the core of a chemical regulation. There's some alternatives assessment that's performed under REACH, but it's not a kind of a do not pass go, you know, choke point in the regulation. It's not a core function of the regulation the way it is in California.
Thank you. Another question we have is, can you clarify whether 90% reduction in Roundup occurred in San Francisco? Was it just among city government?
Yes, this is only looking at public use of the chemical. So what's, sorry, we'll have to page back through to the end, but all of those uses that they identified, which is where the, you know, government gardeners are working. Whoops, do this. Oh, it went all the way to the end. Let's see if I can actually use this to skip forward. And here, actually to here. So it didn't necessarily reduce it in private lawns and gardens, but in public parks, built environment, median strips, airport runways, and natural areas that are in the city or county boundaries where they were working to do invasive weed control. So the 90% reduction came by using these alternatives, except in median strips, natural areas where invasives were a problem, and the airport.
We have a question from somebody who's watching live on Facebook. Do you have any students who will be presenting on their current work anytime soon?
Unfortunately, we just missed. On Monday, we had an all-day presentation of a whole bunch of our interdisciplinary projects done by our graduate students at Berkeley Center for Green Chemistry. So one thing that you can do is go to the Berkeley Center for Green Chemistry website and sign up for our mailing list, and you'll get notification about future events. Every year at the end of our Greener Solutions fall course, we have a public presentation of those projects that occurs in early December. It's usually around December 6th or 7th. And we send out a notification to our email list. So if you get on our email list, and if it's not evident from our website how to do it, you can email me, and I'll get you in touch with the right person. And then finally, we do, because all of our Greener Solutions project work is publicly available, it's posted on our website. So if you Google Berkeley Center for Green Chemistry, Greener Solutions, it'll get you right to the Greener Solutions page, and you have to do a little scrolling and clicking through, but you can find most of our past students' work there.
Well, thank you so much. It's now 11:30. We had one question which was about what were examples of similar university programs to Berkeley's Green Chemistry program and sources of funding. And so I'm not sure if you have time to quickly give an answer to that, but that's probably our last question we could answer given time.
There are other programs that are doing green chemistry in chemistry labs. Leeds in London, Yale has some interesting work going on, and University of Oregon has great green chemistry happening in chemistry labs. There's very few programs that are doing interdisciplinary work the way we do. It's sort of our founding principle, and this kind of deep integration of environmental health sciences with chemistry and engineering and toxicology is unique.
Well, thank you so much for this really great presentation. We really appreciate your time and sharing this important knowledge with all of us. So thank you very much, and thanks to everyone who joined us today for today's webinar.
Thanks so much for having me.
You're welcome. Bye-bye.